Okay, so first off, what is, I'm going to turn this off because otherwise there's a group chat going. That might keep going. Okay, so first off, what is oxidation and what's reduction? Let's see. Got the chat pulled up so I can see if you guys type things to me. So oxidation, I know a lot of times the professors will give you guys the oil rig example. Perfect. Yep. Actually, you have those backwards right now. Those actually do confuse me. So it's oil rig is one way people memorize that. And so that is oxidation is loss of electrons. And reduction is gain of electrons. So some people remember it like that, and that's perfectly fine if that works for you. I personally remember it a different way. How I like to remember it is that reduction reduces the charge, so oxidation is just going to be opposite and it's going to raise the charge. So that's how I remember it. I think of it as reduction reduces charge. Because then it's more, I guess, intuitive if you look at it that way, because it says reduce, it should mean something is getting smaller, and so then it actually is getting smaller that way. So that's how I choose to remember it. So oxidation is increases charge. Okay. So we're going to label the oxidation state for each of the elements in the following compounds. So we'll look at some of these. Let's see. I think it may be easiest if I just type past on this. So with that, so we'll have C. No, I'm going to do it below. I like that better. That will work. So we're going to have, so C is going to equal what? And O is going to equal what? We'll leave out spaces so it doesn't take up as much space there. Oops. So how we figure this out is unless it's a peroxide, oxygen's always -2. So we know that that's going to be a charge of oxygen. But whenever we look at, the carbon, we have to figure that out from the oxygen. So we can look at that and go that we know the charge overall is 0 because they don't list one here. So we know that oxygen is -2 and there's 2 of them. So 2 times -2 is -4. And so to get to the 0, we're going to have to cancel out that -4 with a +4 from carbon. So that's how we can kind of figure out those. So with this one, carbon is going to equal what? And oxygen is going to equal what? So see, we have the same elements, but they're just in different proportions. So just like before, oxygen is going to be automatically -2. So we know that much. But then we have to go to the carbon. And so because we know that the oxygen is -2, we can take that and we can say, okay, so our total charge is 0. And so 0 is going to have to equal the two charges added together if you want to like look at it written out like that. And so, you know, oxygen is -2, so we're going to have whatever carbon's is plus -2, so -2 is 0. So whenever you add 2 to both sides to cancel that out, you end up with carbon is 2, if you do it that way. What do you think the oxidation number for, or the oxidation state for carbon is in this? Oh, it looks like I have one more person join on here. If you wouldn't mind, please send your UID and full name just privately to me. So because carbon is just by itself, it's going to have a charge. Its oxidation state is going to be 0 because the charge is 0 and there's nothing else going on here. So that's all we have to look at. Let's see. There we go. So for so for this one, we're going to have to figure out carbon and hydrogen. So we automatically know that hydrogen is always going to be -1. And so we're automatically going to go ahead and be able to put that in. So just like before, we're going to have to go, okay, our overall charge is going to be 0 because they didn't list a charge. And we can tell that hydrogens, we don't know carbons yet, but we know that hydrogen is -1, but there's 4 of them. So we're going to have 4 times -1. And so whenever we solve that, oh, that's weird. Okay, whenever we solve that, we end up with, sorry, I missed my thing. We end up with 4 for carbon because it has to cancel that out. And carbon's one that'll generally be 4. It shouldn't really change for the most part. Oops. So now we're looking at NaCl. In NaCl, you can look at a periodic table, and just from where they're at with Cl being in the 7th group, group 7A, then you're going to be able to see that it is -1 for oxidation, just because that's typically where it'd be, and that sodium, with it being in the first column, it's going to make it a +1 just to even those out, and that automatically cancels out. So some of them are just really simple like that, and they're automatically what they look like they would be. And that's the way most of these have been so far. So yeah, so I have sodium. It's +1. I guess I should be putting that in positive. And then we're gonna have chlorine is -1. Okay. So then over here, we're gonna have to do this one. This one's a little bit more complicated. So just like before, we know that oxygen is going to be -2. Oops. So yeah, oxygen is -2. And K is in the, potassium is in the first group, so that makes it +1. And then manganese is going to be one of those strange ones. Oh, that's not what we're trying to do. This might just act weird for us today. I'm take that a little smaller so it doesn't do something weird. So manganese is one of those weird ones. It's in the transition states and has multiple different possible oxidation states. And so we can use these other numbers to figure that out though. So we see the overall charge is 0. We have 4 oxygens that all have a charge of -2. So that's when we multiply the 4 and -2 together, we have -8. But then we have a +1 charge from the potassium. So we're at -7. We do the 1 minus 8 there. And so then we know that this has to cancel that out, so it's going to be 7. Okay, now we have our zinc oxide here. Oh, actually, I need to go back. There we go. Okay, cool. So we have our zinc oxide here, and just like before, oxygen is always -2. So then we're going to use that to figure out the zinc, and since it's just 1 oxygen and 1 zinc and no charge up here, then it's going to be automatically +2. Put that in here. Okay. So actually, I'm going to go ahead and change this one. So actually, I'll leave it. But so we'll go ahead and do this. So we know oxygen. I'm going to go ahead and change this actually. I'll talk about it first. So, but we know oxygen is -2 and hydrogen is always going to be either negative or +1, and it's +1 this time because it's first and has to cancel out the oxygen there. So that one's pretty simple. I'm going to make this H3O plus just so you can see an example with one that has a charge. Oops. So we're going to change that up a little bit. So with you looking at that, we have to figure out what hydrogen and oxygen equal. And kind of like before, you have to make everything equal the charge. So if you have the charge of +1, so you're going to have 1 equals whatever's here. We know oxygen's -2, like always, unless it's in a peroxide. And then, so we need to figure out hydrogen. So we have 3 times H plus -2, or just -2. So when we move this -2 over, we have to add it to both sides. So then we end up with 1 plus 2, so then that's 3. So you have 3 times 3H, and it makes the hydrogen +1, which you know that because it's hydrogen is always going to be, like I said, plus or minus 1. But that's how you would solve it to figure that out if it does have a charge. So, what do you think the charge is for this oxygen here, or the oxidation state? This one's being weird. Let me type to the side for this one. So you know the charge is 0, and there's 3 oxygens, which you would think be -2 because they always are. But if it's oxygen by itself, like it is here, there's nothing they can really be interacting with, so it just means it's 0. And that's it. And that one is an O, but the O and the 0 look the same, so. All right. Okay, leave that so you can see it for the time being. Okay. So for the following reactions, label the oxidizing and reducing agents. So we're going to look at these and we have to figure out what is being oxidized and what's being reduced. So when we look at this first one, let's see here. I'm gonna, because I can't really draw arrows easily on this, unless, I guess I can actually. It's just really temporary. Yeah. Okay, I can draw an arrow, but I'm gonna go ahead and do this so you can see it, and it'll stay there. So I'm gonna color the, let's see, we're gonna highlight the oxidizing. Okay, so first, I'm gonna go ahead and write something, just make some simple. So if something is oxidized, so when a compound is oxidized, it's the reducing agent. And you guys probably already knew that, but just in case you didn't, I'll go ahead and add that here. And when a compound is reduced, it is the oxidizing agent. And so that's a little bit counterintuitive. And the reason it's like that is because they always come in pairs. So what I'm going to do is I'm going to highlight them so we can kind of see what's what. We'll make the reducing agent red, I guess. And oops, it didn't work. Let's try it again. Yeah, there we go. We're going to make the reducing agent red. And we're going to make the oxidizing agent blue. You have a little bit of a lighter color, so that's a little bit easier to read. There we go. You like this? There we go. Okay. So with this first one, we're going to look at it. It's easiest if you look at like these first ones are kind of by themselves. So you have aluminum by itself. So anything by itself, its oxidation state is 0. So we're going to look at that, and we're going to see how aluminum changes. And over here, I don't know if you've noticed this, but with compounds, it always lists the positive ones before the negative ones, like oxidation state wise. So like oxygen, has this state of -2, and there's 2 of them. So that means this manganese would have to be in -4. So because we know that, we know what's going on with that. We know what's positive, what's negative, but it's always the positive one before the negative one. So this is 0, so it's by itself. So even if say you're in an exam, you're kind of rushed, and you don't really want to take the time to figure all these out and ask a question like this where you don't have to know the exact charges, then you can go ahead and just go, okay, well, aluminum's positive here because it's listed first, and oxygen's always negative anyway. So we know that aluminum's charge is going to be increased. So it's going to be oxidized because its charge is increased from here to here. So aluminum is oxidized, therefore it is the reducing agent, which makes it red. And so we're going to do that. And then here we go. So then we're going to look at manganese here. And because it's first, we can tell it's positive. And because it's by itself here, we can tell it's 0. So going from positive to 0 means that it's reduced. And because it's reduced, it's the oxidizing agent. So this one is reduced, and it's oxidizing agent. So we're going to make it blue. Oh, that's not the blue it is. Here we go. So, got that. So now we're going to look at the hydrogen and the copper here. So first off, let's look at the hydrogen. So here it's going to have a charge of what? No, not quite. Not -1. So I can tell you why it's not -1 is because it has a charge of 0 and it's an element by itself. So it makes it 0. Perfect. So then we're going to look at it over here, and it's with oxygen. That's always -2. And so that means it's going to have to be positive, plus it's in the front, which makes it positive. So you know that's going to go from 0 to a positive number. So is it oxidized or reduced? No, because we are gaining charge. So it's not going to be reduced. It's going to be oxidized. But it is going to be, because it's oxidized, it's going to be the reducing agent. Does that make sense, or do you have a question with that? All this is a little bit confusing because everything's kind of backwards of what you would expect. So we're going to look at the copper here. So copper is in the front here, meaning it's positive and it's with oxygen, which has a state of -2, making the copper have one of +2 right here. So we're going to go from positive over to here, where your copper is by itself, so has a charge of 0. So is this copper going to be oxidized or reduced? Yep, it's going to be reduced. Perfect. So, which makes it the oxidizing agent because those are backwards. It's the one making the oxidation here happen. So like if this was by itself, just a hydrogen and H2O, it wouldn't automatically like have this reaction. So it has to have this oxidizing agent to make that happen. And the same the other way around. Like if you just had the copper oxide and the if you just had like your copper oxide and your copper here, then it wouldn't just automatically happen. It has to have that reducing agent to reduce it. And then also you can kind of look at the one that's oxidized is the one that gained the oxygen. That doesn't work in every reaction because not every reaction has oxygen, but that's how a lot of them are. And it's called oxidized even if there's not oxygen, which is strange, but that's how it is. Okay, so let's look at the iron oxide here first. So we're going to be looking at the iron. So is iron going to have a positive or negative charge here? Positive, perfect. Okay, and is it going to have, what kind of charge is it going to have here? Or oxidation state, not charge. I apologize, I'm using the wrong terms. 0, perfect. So if it goes from positive to 0, is it oxidized or reduced? Reduced. Perfect. Yep, so this is reduced, which like we talked about, makes it the oxidizing agent. And let's see. And these all just all happen to be listed in the same order, but that's not always going to be the case. They can list them in the other order too. It would be just the same if it had H2 before copper oxide here. And therefore we're going to look at this, and our hydrogen is by itself, so it has a charge of 0, like we're talking about. And it's going to come over here where it's positive, so it's in the front, and it's with oxygen that's always negative. And so it's oxidized, making it the reducing agent, and it gained oxygen, so it's oxidized. You can look at that either way. Okay. So. That's kind of strange. Okay, so then we're going to come look at this. So would you use an oxidizing agent or reducing agent for the following reactions to occur? So to figure that out, we need to figure out if the reaction, if what's happening here is oxidation or reduction, and then we're going to have something to make that happen. So okay, so we have ClO3 minus and ClO2 here. So we're trying to figure out the chlorine here and figure out what the oxidation state is on both sides. So what is going to be the oxidation state of chlorine on this first part here? Looking at this one. So -1 is the charge, but that's not going to be your oxidation state. Oh, and yes, it will have a positive charge. Just saw that question. And so just so you know, oxidation and reduction doesn't always go from like positive to 0 or 0 to negative or like or positive to negative or something. It can go like just they can both be positive and it just be higher or lower numbers, or they can both be negative and be higher or lower. And you just have to go, does the charge increase, does the charge decrease, and look at it that way. So to figure out the chlorine, we know the -1 is our charge, and we know oxygen is -2, and we have 3 of them. So we're going to have 3 times -2 for that. And then we're also going to have chlorine, but we don't know how much that is. So we're just going to add whatever the oxidation state of chlorine is. So 3 times -2. So that's going to be -6. And we're going to have to move this over to the other side. Close. Okay, so 6 would be the charge if, or not the charge, 6 would be the oxidation state if the charge was 0. But because we have this charge of -1, when we add the 6 to both sides, 6 plus -1 is 5. So we know the oxidation state of the first one is going to be 5. So that's for the first side. We know it's 5. So then for over here on the second part, you're going to do this, try to figure out what is going to be your oxidation state for the chlorine over here. 4. Perfect. Perfect. So it's 4 right here. Okay. So is the oxidation state increasing or decreasing? So actually, it is an oxidizing agent. So this is being reduced, we can see that. So this is an oxidizing agent, but what it's asking is, would you use an oxidizing or reducing agent for the reaction to occur? So because it is reducing, we would need a reducing agent to make it actually reduce, if that makes any sense, because this is the oxidizing agent. So because we figured out, we know that this is a reducing, or needs a reducing agent. Okay, let's see. So for B here, we're going from SO4 2 minus to just S2 minus. So what is your oxidation state going to be for sulfur in this first one, in SO4 2 minus? Six. Perfect, perfect. Does everyone else understand that, or do we have any questions? All good. Cool, cool. Okay, so what is the oxidation state going to be for sulfur in S2 minus? -2. Perfect. Okay, so so just looking at that, do you think it's going to need an oxidizing or reducing agent to help this occur? So it is, so because this is being reduced, it is an oxidizing agent. So it needs a reducing agent to make this reaction happen. So kind of like, y'all see me get this backwards, which is confusing, so I get that. So it's kind of like up here, when we're looking at this. So see how they're always paired? You have one that's being reduced and one that's being oxidized each time. And so you have an oxidizing agent and a reducing agent each time. So whichever one you have, you're going to need the other one. Is what we're looking at down here. So kind of like looking at this first one, this is being reduced. So if we were just had this like MnO2 with an arrow pointing to 3Mn here, we could see that the charge is being reduced, getting lower. So we know that it needs a reducing agent to make that happen. So the aluminum is our reducing agent here that they added to this reaction to make it happen here. Does that make sense? Okay. So because this is being reduced, it needs a reducing agent to make it be reduced, because this isn't like just going to happen like naturally, I guess. We're going to have to like make this reaction happen. Okay, so now we're going to look at zinc to zinc chloride here. So what is the charge of zinc? or not the charge, I keep saying that, I apologize. What is the oxidation state of zinc? In that one. Y'all know this one, we've talked about it. It's an element by itself with, so it's just going to be whatever the actual charge is what the oxidation state is going to be. So because it has a charge of 0, it's by itself, so it's just going to be 0. What is the oxidation state of zinc in zinc chloride here? It would be a positive number, that's correct. So looking at that, if you know it's a positive number, you don't even actually have to figure this out. But yes, you are correct. So then you would need an oxidizing agent. That's correct. And just because we haven't really looked at these much without the without having oxygen, like the ones we were looking at up here, they all had oxygen for the most part. We're gonna look at this real quick. So, you know, because zinc is one of those that's kind of in the middle, can change some, doesn't always have to be the same. So, because this is in the 7th group, you know that chlorine is going to have the oxidation state of -1. So -1 times 2, you have -2, and you're going to have to add that to the charge to move it on to the other side. So then you have just 2, because you have 0 for the charge, plus 2. So you know the zinc is 2 over here. What is oxidation state of manganese in this first part of the reaction? Two, perfect. And then in the second part, what's it going to be? Oops. It's going to be 4, perfect. So is I'm going to need an oxidizing or reducing agent? Oxidizing, perfect, because it's being oxidized, so it needs an oxidizing agent to make it be oxidized. Okay, so we're going to write balanced equations for the following reactions. And we may not get through all of these because it's getting, we have 20 more minutes left. These are kind of long. I don't know, we might. We'll see what happens. So we're going to start with this first one here. So with the these equations, because when you have to balance them, you're going to have to separate them into the two halves of the equation, and you're going to separate into the oxidizing reaction and the reducing reaction. But the thing is you honestly don't really have to know which is which during this part. You can just go ahead and break it up and go, okay, so we have, obviously, you know, CrOH3 is going to go with CrO42 minus. And so since we know that, we can just go ahead and just look at that reaction. And then we know that these, the Br2 and the Br minus, are both going to have to go together also. So if we look at the CrOH3, oh, that's not what we're looking at. Okay, and as it turns into this, okay, so we're going to have to look at that reaction, and then we're going to have to look at the other reaction as well. So we're also going to have this right here. And it becomes Br minus. So first off, we're going to work with this here. So we have CrOH, and we have a CrO42 minus, and let's see. So first, I did forget the 3. Thank you. Okay. So we're going to have to look at this, and we're going to figure out how to balance them. So first off, we're going to have to add hydrogen to both sides, I believe. Yes. Wait, make sure I'm thinking right here. Yeah, okay. So what we're going to do is we're going to add the hydrogen to both sides to be able to go ahead and get rid of this OH here, I believe. That's what we're trying to do. Okay, so first off, what do we need? We need to have equal amounts of everything on both sides, I guess, is where we need to start. So we have 1 Cr on both sides, so we're good there. We only have 3 oxygens over here, and we have 4 over here. So we're going to have another H2O. That's where we're at. Sorry, I was thinking wrong again. So we're going to have another H2O for this one. To get that extra oxygen. So now we have 3 oxygens here and 1 here, so that's 4 on this side. And we have 4 oxygens here. So that's even now. But now we have a bunch of hydrogen over on the left that we don't have on the right yet. So we're going to have to get these. So we have 3 hydrogen here, 2 more here. So we need 5 hydrogen over on this side to even that out. And hydrogen, I don't know why I just said, hydrogen is going to be, oops, have a positive charge there. So we're going to have to look at this now. And so since we have this hydrogen here, so we have 5 positives and 2 negatives, so we're going to have overall charge of +3 over here on the right, and everything is 0 on the left. So because this is 0, and we need this to also equal 0, then we're going to go ahead and add electrons over here to cancel that out. So we're going to add 3 more electrons to get rid of the +3 charge that we have overall over here. So we're going to have +3 E minus, just shorthand for electrons. So then we have that side of the reaction. And I'm going to go ahead and put what that originally was so you can still see that. And we got that all from this. Cool. So then we're going to have to go deal with this one over here. So what are we going to have to do this to make it into, to make them match? So obviously, first off, we need to have the same number of bromines on each side. And we have 2 on one side and 1 on the other. So we're going to have 2 of these. Okay, so now all of the atoms are equal on each side. But we have 2 times this -1 charge here is going to be a -2 charge on this side when we only have a 0 charge on this side. So because of that, we're going to have to add electrons to even out, and so we're going to add 2 electrons over to this side. So we're going to add 2 E minus. So now we have the reactions, both the oxidizing and reducing, the oxidizing agent and the reducing agent have both been like, no, that's not how you phrase it. The oxidizing reaction and the reducing reaction are both like balanced now. So now we have to add the 2 reactions together and balance them. So we're going to add this one and this one together. So we have this plus, so everything before the arrow added together. Okay, and then we're going to have everything after the arrow. Yeah, so here we are. So we have this. Plus everything after the arrow for this one. Okay, so now we're going to have to look at this. And first off, we need to look at it and make sure you have the same number of electrons on both sides. So we have 2 electrons on this side and 3 on this side. So we're going to multiply this whole side by 2. Oops. And we're going to multiply the other side by, oh no, 3. Apologize. Okay, this one by 3. And this one by 2 in order to make those equal. Okay. Here we are. Okay. So when we do that, then actually, go ahead and take that out so you have the original there still. Okay, so when you do this, you're going to end up, you multiply everything by 3 over here. So you have 3 CrOH3, and you have 3 H2O, and 3 Br2, and 6 E minus. And then you've multiplied everything out here. So we're going to multiply this side by 2. So we're going to have 2 CrO4, 2 minus. We're going to have 10 hydrogen ions, excuse me. We're going to have 6 E minus over here. And 4 Br minus over here. So Now everything's been multiplied out. And then we look and we see what's the same. So we have electrons on both sides that we can get rid of. So we have 6 over here that we don't need. And we have 6 over here that we don't need because they're exactly the same, so they cancel each other out. Okay, and then we look, and do we have anything else that's the same? No, we do not. So here we go. We have that, and then look here. Think we're good to go. Okay, so then we have that. Okay, so now this is going to be our final answer here. We might be able to get through one more of these before 4:30. Okay. So we're going to have this one. Once more, you need to divide it into the two reactions. So we're going to have this one going with this one. And so then we're going to have the hydrogen, or our hydrogen peroxide there, and our oxygen here. They go together. So we got. Whoops, that's wrong. But we don't need that plus. We do need this though. And then the other reaction we're going to deal with is going to be this right here. So we're going to have this be turning into this right here. Okay. So looking at this, we have to figure out how to balance it once more. So we have 2 oxygen on both sides. We're doing good there. We have 2 hydrogen on this side and on this side. So just like before, we're going to add our H+ ions. We needed 2 of those. Only put 1. So we have 2 H+. But then we look at this and we have to make sure our charge is equal because all of our elements are equal. So we have overall charge of positive 2 here because we have 0 plus 2 positive 1. So positive 2 here and 0 here. So we're going to have to add electrons to this side to decrease its charge to match the other side. So we're going to have plus 2 electrons. Whoops. There we go. Okay. So then we have that. So then we're going to have our 2E minus and our 2H plus. Those cancel out. So now we just have 0 equals 0. So we're good to go there. Everything's all balanced. On this one, so we can see we have the SB on both sides, and that's already equal. Got 1 of each. And we can see that we have oxygen on this side, but not on this side. And we need oxygen over here, but you can't just go adding oxygen because it has to be something it gets from the solution is what you can add. So we can add hydrogen to, or not hydrogen. Yeah, we could add hydrogen over here because we get it from the solution, but that's why we can't just add oxygen. So we have to add water to get our oxygen. So we need 2 oxygens, so we're going to need 2 H2Os. Okay, so we have our 2 oxygens, but now we have 4 hydrogens over here. And we did not need 4 hydrogens. So we're going to have to go over here And we're going to add plus 4 H2Os. Whoops, that's the wrong button. Oh no, we're just adding H's, not H2Os. Sorry. And H pluses. Okay, so now what are our charges looking like? So our overall charge over here, 0, once more. Over here, we have -1. So we have 1 negative, and then we have 4 positive here. So -1 plus 4, and we have a charge of overall charge of 3 on this side with 0 on this side. So we have 3 more on this side than the other side. So we're going to go ahead, just like before, add our E minus. So we have 3 E minus. Okay, and then that is going to be all balanced out at that point then. So we're good to go there. Then we're going to go ahead and add the two sides together again. So we are going to go ahead and have this on this side. And this on the other side. Or not the other side, the same side, because it's still on the left of the arrow. And then we're going to have this. Oops. And plus everything on the left side arrow over here. Okay. So we have all of that. And we need to figure out what cancels out again. So so we need to cancel out our electrons. We have 2 on one side and 3 on the other. So once more we have to do our multiplication. So we're going to multiply this side by 3. And we're going to multiply the other side by 2. We should be a few minutes over time. This is almost done with this one. And I encourage you to go try the others on their own. I think we're gonna have a test prep Monday. Is what we're gonna do at probably 6 or 7 p.m. is whenever I'll end up doing that. Probably 6 o'clock on Monday. We'll do 6 o'clock Monday for our test prep. I'll go ahead and put this in here. Okay, so you multiply everything out again. Actually, here, I'm just gonna do that because I already had the other. So this is times 3. 2 times 3 is 6. 2 times 3 is 6. 3 and 2 times 3 is 6. So then this one's multiplied by 2. So 2 H2O2. Do that. 4 times 2 is 8. And 3 times 2 is 6. So we have all this. To look at what cancels out again. And oops. Oh no, I already did that. Okay. So we have our electrons, which was what we were trying to cancel out. So those will cancel out. We have 6 on both sides. Okay. And then we look, oh look, we have hydrogens on both sides. So if we have 6 H plus ions over here and 8 over here, that means we can completely get rid of these 6. And we can get rid of 6 of them over here. So 8 minus 6, and we have 2 hydrogens left on this side. Then aside from that, we don't have any oxygen on the other side. We don't have any SBs. We don't have any waters over there. Okay, so we should be good. So then we have this as our final equation. All right, there we go. Um, okay, well, if you guys have any questions, feel free to ask. I'm gonna go ahead and end my recording for today.